Imagine a world teeming with tiny particles constantly in motion. These particles, the building blocks of matter, hold the key to understanding heat and temperature. The kinetic particle model explains the behavior of matter at the microscopic level. They are in perpetual motion, vibrating, rotating, and colliding. It explains why solids hold their shape, liquids flow, and gases expand. The kinetic particle model is a cornerstone of our understanding of matter. The kinetic particle model, a cornerstone of modern physics, postulates that all matter comprises minuscule particles in perpetual motion. These particles, far too small to be seen with the naked eye, are the fundamental building blocks of everything we observe in the universe. This model revolutionized our understanding of matter by providing a framework to explain the behavior of solids, liquids, and gases. It posits that the state of matter is determined by the arrangement and motion of these constituent particles. In solids, particles are tightly packed, vibrating about fixed positions. This rigid structure gives solids their definite shape and volume. Liquids, on the other hand, exhibit particles that are more loosely arranged. They can move past one another, resulting in the characteristic fluidity of liquids. Gases, with their widely spaced particles, exhibit the greatest freedom of movement. These particles move rapidly and randomly, colliding with each other and the walls of their container. This constant motion explains why gases expand to fill any space they occupy. The kinetic particle model beautifully explains the different states of matter based on the arrangement and motion of particles. In solids, particles are tightly packed, like dancers in a crowded ballroom with limited space to move. They vibrate about fixed positions, maintaining a rigid structure. Liquids, however, resemble dancers with more freedom to move around the dance floor. The particles are less tightly packed and can slide past each other, giving liquids their fluidity and ability to take the shape of their container. Gases, in this analogy, are like dancers with boundless energy, free to move throughout the entire space. The particles are widely spaced and move rapidly in all directions, colliding with each other and the walls of their container. This explains why gases have no fixed shape or volume and expand to fill their container. The transitions between these states of matter, such as melting, freezing, boiling, and condensation, can be explained by changes in the energy of the particles. Adding energy, usually in the form of heat, increases particle motion, causing them to overcome the forces holding them together. Imagine a bustling dance floor filled with dancers moving at various speeds. Some sway gently while others twirl and leap with vigor. Temperature in the realm of particles is akin to the average kinetic energy of these dancers. It reflects the intensity of particle motion within a substance. A higher temperature signifies a greater average kinetic energy of the particles, implying a more energetic dance. Conversely, a lower temperature indicates a less frantic dance, with particles moving at slower speeds. Temperature is not a measure of the total energy within a substance, but rather a reflection of the average kinetic energy of its constituent particles. It quantifies the hotness or coldness of an object and determines the direction of heat flow. Just as a lively dance can energize the entire room, a higher temperature object can transfer heat to a lower temperature object. This transfer of thermal energy continues until both objects reach a state of thermal equilibrium, where their temperatures are equal. Section 5. Thermal energy, the collective energy of particles. Imagine a grand ballroom teeming with dancers, each possessing a certain amount of energy. The total energy of all these dancers combined represents the thermal energy of the system. Thermal energy encompasses the internal energy of a system associated with the random motions of its atoms and molecules. It is the sum of the kinetic and potential energies of all the particles within a substance. Kinetic energy is the energy of motion, reflecting the speed at which particles are moving. Potential energy, on the other hand, is stored energy due to the relative positions of particles and the forces between them. The thermal energy of a substance is directly proportional to its temperature and the number of particles it contains. A larger object at the same temperature as a smaller object will possess greater thermal energy due to its greater number of particles. Understanding thermal energy is crucial in various fields, from engineering to meteorology. It helps us comprehend how heat flows, how engines operate, and how weather patterns develop. Section 6. Kinetic energy, the energy of motion. Picture a lone dancer gliding across the dance floor, their movements fluid and graceful. The energy possessed by this dancer due to their motion is analogous to kinetic energy at the particle level. Kinetic energy is the energy of motion, inherent in any object or particle that is in motion. It is dependent on the mass and velocity of the object. A faster-moving object possesses greater kinetic energy than a slower-moving object of the same mass. In the realm of particles, kinetic energy is a measure of their average translational motion. The higher the temperature of a substance, the faster its particles move, and the greater their average kinetic energy. This kinetic energy is responsible for various phenomena, such as the pressure exerted by a gas, the diffusion of particles, and the transfer of heat through conduction. It is a fundamental concept in physics, underpinning our understanding of motion, energy, and heat. Section 7. Heat energy on the move. Imagine two dancers, one filled with boundless energy, the other moving more sedately. As they come into contact, the energetic dancer's movements naturally transfer some of their energy to the calmer one. This transfer of energy, in the context of particles, is akin to heat. Heat is not a property possessed by an object, but rather the transfer of thermal energy between objects or systems at different temperatures. It always flows spontaneously from a region of higher temperature to a region of lower temperature. This flow of heat continues until thermal equilibrium is reached, where both objects or systems attain the same temperature. At this point, the net transfer of heat ceases and both objects exist in thermal harmony. Heat can be transferred through three primary mechanisms: conduction, convection, and radiation. Conduction involves the transfer of heat through direct contact, convection through the movement of fluids, and radiation through electromagnetic waves. Understanding heat transfer is crucial in various applications, from designing efficient insulation for homes to developing effective cooling systems for electronic devices. Section 8. Internal energy, a system's total energy. Imagine a bustling dance floor alive with the energy of countless dancers. Each dancer possesses kinetic and potential energy. The sum of all these energies represents the internal energy. Internal energy is the total energy within a thermodynamic system. It changes through heat addition or removal and work done on or by the system. Section 9. Mechanisms of heat transfer, conduction, convection, and radiation. Imagine a group of dancers huddled close together, their body heat transferring from one to another. This intimate exchange of thermal energy mirrors the process of conduction. Conduction is the transfer of heat through direct contact between objects or substances of different temperatures. It occurs when more energetic particles collide with less energetic particles, transferring some of their kinetic energy. Convection, on the other hand, involves the transfer of heat through the movement of fluids, such as liquids or gases. As a fluid is heated, it becomes less dense and rises, while cooler, denser fluid sinks to take its place, creating a convection current. Radiation, the final mode of heat transfer, requires no medium and can occur even in a vacuum. It involves the emission of electromagnetic waves, such as infrared radiation, which carry energy away from the emitting object. These three mechanisms of heat transfer play crucial roles in various natural phenomena and technological applications. From the warmth of the sun reaching Earth to the cooling of electronic devices, understanding these processes is essential. Section 10. The significance of thermal physics. The kinetic particle model and the concepts of thermal energy, temperature, heat, and internal energy form the bedrock of thermal physics. This branch of physics explores the relationships between heat, work, temperature, and energy, providing a framework for understanding the behavior of matter at the macroscopic and microscopic levels. The principles of thermal physics are ubiquitous, influencing countless aspects of our lives. From the design of efficient engines and power plants to the development of new materials and technologies, the applications of thermal physics are vast and far-reaching. Understanding heat transfer mechanisms is crucial in various fields, from architecture and engineering to meteorology and climate science. It enables us to design buildings that are energy efficient, develop effective cooling systems, and predict weather patterns. As we delve deeper into the intricacies of the universe, the principles of thermal physics continue to illuminate our understanding of the cosmos. From the birth and death of stars to the evolution of planets, thermal processes play a fundamental role in shaping the universe we inhabit.